Well, good afternoon. Let's go ahead and get started. I've got 12:30 anyway. One announcement for today, that is the lab schedule. I apologize for all the changes. However, you should know that next week is lab number 10. The following week is lab number 9. Then the lab practical. Labs 9 and 10 are each a little bit shorter. And so on lab number 10 next week at the beginning, I will give you all the details that you are allowed to know about the lab practical as well. And so, because the idea is you go into the lab practical with a certain set of information, and I want to give that to you next week. As far as exam 2, grades were in general good, and so I would not expect a curve. There's only 4 weeks left, then finals, so we're coming down to it. And good news is we're right on schedule, believe it or not, although the schedule has changed a little bit for labs. Lecture, we're right on schedule to finish everything we need to know without hurrying up, meaning that we will have time for questions just like we always have had in lecture. We will have homeworks. That is true each of the next 3 weeks, culminating in exam number 3 and then the final. So. Now, as far as lecture, I hope to finish almost all, if not all, of chapter number 9. And as far as chapter number 9 goes, we were about to talk about this slide here, phosphorus, sulfur, and all of the 3p area elements, and all of the elements with higher atomic numbers can have expanded octets. Can have expanded octets. And now that's the general theme. The reason we will have expanded octets for these elements is to minimize formal charge. And one of the rules we had from last lecture was that the best Lewis structure has the least amount of formal charge possible. And so we will use expanded octets, as we will see. A good example is write the best Lewis structure for the sulfate ion. And you may or may not have done this in Chem 300. If you did, you would complete octets in the following way. You would have sulfur bonded singly to each of the 4 oxygens, and then you would sprinkle all your electrons around. Until you got to a place where all of them had octets, and you put square brackets around it, and at least in general, for Chem 300, that's where you'd stop. And you might find this answer on the internet because that is where some people stop. We're going to go one more step. The step is to make the best Lewis structure. That's the Lewis structure with the least amount of formal charge. If we were to evaluate the formal charge, we would see that each oxygen, well, oxygen, let me remind you, has 6 valence electrons from the periodic table. It has 1 bond and 6 lone electrons, so that's going to be 6 minus a total of 7. Each of these oxygens has a formal charge of -1. And you can go through the process of determining the formal charge for sulfur. When you do, again, it has 6 electrons, valence electrons from the periodic table, only 4 bonds, and no unshared or lone electrons. This one's +2. And that is a lot of formal charge inside this Lewis structure, and so it is not the best. How to find the best is we will use what's called an expanded octet. An expanded octet means that sulfur, and it's here where I'm delighted to be able to get out my pointer finger. here we come over to the periodic table. Here's sulfur right here. So these elements in the group 3p area and the elements below them can have expanded octets. And while it is true that the most common ones will be chlorine, sulfur, and phosphorus, then occasionally you'll see bromine and iodine and selenium as well, having expanded octets. Note, 2p area, boron, carbon, nitrogen, oxygen, fluorine, and neon, should it ever bond, never have expanded octets. They will always have what's called an octet, which is what we're used to. So what's new is you can have an expanded octet. Those expanded octets, this is how it works. I'll do it in red. An expanded octet means that you have more than 8 electrons, and it doesn't matter which oxygens you choose them from, but form double bonds towards the center. When you form a double bond from something that has a negative formal charge to something that has a positive formal charge, both of them end up being closer to 0. Doesn't matter whichever one you do it twice though. And what you end up with, besides the red pen that doesn't work too well, let's try blue. Let's go. See if this is working better. So there's the double bonds I just made by moving those electrons. The other oxygens still have single bonds. And then we fill in all of our electrons. You don't have to be this careful. I'm not always, but I try to be. So this pair of electrons up here made the double bond, so I'll leave the other ones where they were before. And this is something that I don't really care about, but it helps my process to do it this way. But as long as they have the right numbers of electrons, everything's good. And I'll jump in here with the fact that Lewis structures always show all electrons. And this is all of the electrons here. I tend to put brackets around them oftentimes. And now I do a formal charge analysis. And since these two oxygens have not changed, they still have the same -1 formal charge. And if we do an analysis, the oxygen here, and the sulfur will all have 0 formal charge. And you don't have to note that. You will only have to note, and it says this, it'll say, note all non-zero formal charges. A couple other things I'll say about this is, if you can use the brackets or the formal charges or both. Any of those is fine. Actually, as we get towards the end of the class and as you move towards organic chemistry, you won't use the brackets anymore. You'll just note the formal charges. So please, that's fine as well. What I'm looking for is when you draw a Lewis structure, you show me that there is charge in that species and that you recognize that. Because the SO4 with no charge is an entirely different species, an entirely different Lewis structure. In fact, it may or may not exist. This is the best Lewis structure for sulfate. This is the correct one. Any questions about this? How many electrons do we have around the central sulfur atom? Including all bonds, and each bond is 2 electrons, right? We have 12. That's an expanded octet. An expanded octet is anything more than 8. They will be in even pairs because they will be bonds. So 8, so expanded octets will be 10, 12, 14. I've never seen a central atom with 16 electrons around it, but up to 14 I have, and you will. All right. Well, maybe one of your questions is, where do you put all those electrons? An octet, if you'll remember, tends to be associated with a filled s and p orbital. S holds 2, p holds 6, that's 8, done. Well, the CHEM 400 version of this says the following. The extra electrons in the expanded octet is associated with the d orbitals. And by associated, what I mean is that's the closest thing to the truth you're going to hear in Chem 400. It is, of course, more complicated than that, but it is relatively close to the truth. And it does help us explain the bonding that's observed in the structures. So, now, let's get back to one other point, which is where in the periodic table does this happen? I said the 3p area and all lower. 3p is in the n equals 3. Is there a d sublevel? Yes, there is. And so one way to remember that, and actually, again, closest to the truth that we're going to get, whatever that is in Chem 400, yes, the 3p area can place electrons in 3d and have expanded octets. What about the 2p area? Is there a 2d sublevel in this universe? No, and so they cannot have expanded octets. Bodhi question.
So the 3p level can place electron into 3d?
Yes.
Why not 4s?
Oh, 4s, well, in theory maybe it could, but since we're talking covalent bonds, those elements over there, oh, why not 4s? Like, okay, we had this whole discussion about 3D versus 4s. And we said that they're close in energy, right? And so electrons always go to the lowest energy position. And the first thing I'm telling you is they go to 3D. And the next thing I'm going to tell you, and this is an answer that we'll hear more about in Chapter 10 when we talk about shapes, but when you look at the shapes, we'll be able to hybridize, it's supposed to be 2 air quotes there, hybridize. The easiest hybridization occurs when n is the same. So the 3s4d, yes, they're close in energy. And then when they hybridize to make shapes, what will turn out to be true is that it's lowest energy if the n value is the same and their sizes are approximately the same. It'll be tougher to hybridize orbitals where one is n equals 3 and another is n equals 4, which is much bigger. So that's not a great answer, but I understand the question, and as close to the truth as we're going to get, probably, certainly until Chapter 10, is that n has to be the same typically for hybridization to occur. To hybridize, when we talk about that, you will be hybridizing orbitals that are similar in size. And remember, n equals 3. Here's my picture of n equals 3, 3s, 3p. 3d is in the same volume, so I don't know, it motivates it anyway. Any other questions? And so the key take-homes are which atoms can do it and which atoms cannot. And you'll see both of those on the Lewis structures discussion, which I just posted the answer key. You'll see both of those on the Chapter 9. Okay, so next topic, resonance structures. These are structures that have the same layout of atoms but different layout of electrons. A true representation of the bonding cannot be drawn with a single Lewis structure. I said that Lewis structures worked approximately 95% of the time in determining the bonding in molecules. Resonance structures is a case where it doesn't totally work, but we come up with a scheme to understand it. The true representation of the bonding is the average over all resonance structures. Is the average over all resonance structures. And I'll say more about that after I draw some resonance structures for you. The example I'm going to do is carbonate ion. For the carbonate ion, we drew its Lewis structure last time. It has this kind of bonding pattern, and then when we fill in all the electrons, we end up with this Lewis structure here. It's not quite done. Remember, you need some representation of the fact that there's 2 minus 2 extra electrons in there. What I said is you can do formal charges. You can do, well, pretty much, let's just say this. You're always going to do formal charges in Chem 400. You could also do square brackets in charge too if you wanted. But pretty much, you're always doing formal charges because you're always doing formal charge analysis. So this is the best Lewis structure. We said not even that it would want it since it's already 0 formal charge, but carbon can have an expanded octet anyway, so that's fine. Now what are resonance structures? What they are is, when we put this double bond here, we could have placed it in any of these positions. And what resonance structure says is when you have a choice where you put the double bond, draw all choices as resonance structures. So draw all choices for resonance structures. And we have what's called a resonance arrow. I don't really care if you draw it, but when you get to OChem, you will draw it. It's like a double-headed arrow, like that. There's so many arrows in chemistry. But this is what's called a resonance arrow. And for the next one, what I'm going to do is I'm going to draw the double bond here. And for the third one, I'm going to draw the double bond going down. And a couple notes about Lewis structures. The oxygens must always stay in the same places. The oxygens are not moving. It is the bonding that's moving. And that's what I mean. Same layout of atoms, the oxygens and the carbon all in the same, like this oxygen's always going down, one to the left, one to the right. But different layout of electrons. So my double bond is really what's moving. And when I move my double bond, of course my octets still move with them. Let me draw my dots. Typically, I always try and draw my formal charges as far away from all other atoms as possible, but those choices, again, it doesn't matter as long as it's clear which atom it's related to. Question?
So the actual structure of it isn't like a T-shape, it's some three-dimensional shape in this case, but...
Good question. You're asking about what the actual structure is, meaning shape, right? And the answer, so we are very distinctly not talking shape right now. We're talking Lewis structures. And like what I said was, that, so first off, we'll get there. But we want to take all the steps for Lewis structures. And Lewis structures, they can show shapes if you know it, but they don't have to. So no, this has nothing to do with the shape. Lewis structures always show all the electrons, all the bonds and lone pairs, always show the non-zero formal charges, and that's all they have to show. We'll do shape next chapter. And we're really hitting Lewis structures and all the aspects of Lewis structures because your process will always be this. Draw the Lewis structure from Chem 300, do a formal charge analysis to minimize formal charge, then think of resonance, then do shape. And so we got to get all these three parts down first. And then shape, which I think most people hit in Chem 300 as well. We'll add a couple more shapes. But then, but like this is it's the new like grams to moles. It's like this is the heart of everything else we do for the rest of the semester. We'll do it 100 times at least, and we'll feel good about it. So, good question. So many questions that I'm deferring to future chapters. So no shape here. What is important though is that however you draw this first one, all the atoms stay in the same relative positions. If you were to suddenly decide that this O was up here, I would mark it wrong. That's what I mean by same layout of atoms. The atoms are in the same place. Bodhi?
Is there a correct way to lay out the atoms? So like say you did put the oxygen on the bottom on top, would that be wrong?
There is not a correct way to lay out the atoms. So you could put the O up, you could do O, O, O. Yeah, what's important for this step is that however you choose, you know that they're cookie cutters for the atoms for all of them. In fact, just while I'm here, there's no correct positions for these two pairs of electrons. You can put them in any of the positions. You can even put one up here and one down here once we talk about shape, as long as you have the correct number in pairs around each other. Okay, now, the true representation of the bonding is the average over all resonance structures. I want to talk about that. And I want to talk about that by circling two atoms. And I start, because I have the same layouts, I can circle the same two atoms. And what I would say is there's a single bond, a double bond, and a single bond. And the way I like to characterize this bonding is in the following way. There are 4 bonds between the two atoms. There are 3 resonance structures. And it's like between these two atoms, there is a 4/3 bond. So it's the number of bonds over the number of resonance structures gets a 4/3 bond, which is somewhere between a single and a double bond, closer to a single bond. Four-thirds bond, somewhere between a single bond and a double bond, closer to a single bond, because 4/3 or 1 1/3 is closer to 1 than 2. Now let's do the same thing for another one here. In red. In red. How many bonds did I just circle in red? 4 bonds over 3 resonance structures. That one is also a 4/3 bond. And if I did the other one, it would be the same. 4 bonds, 3 resonance structures, 4/3 bond. The average over all resonance structures tells us that each of these carbon-oxygen bonds is a 4/3 bond. each of these carbon-oxygen bond, each carbon-oxygen bond is a 4/3 bond. Those bonds are identical. And so the main take-home message of resonance structures is that when you draw this first one, you must draw all three, and it is the average. So on the exam, can we talk about exam 3 already? On the exam, when there's a question that says, the carbon-oxygen bond in the Lewis structure for carbonate, is it the same as all the other bonds? You would say yes, even though the the Lewis structure shows single, single, double, double. Resonance structures, the point of them is to tell you that all three of these bonds are exactly the same. Meaning, they have the same energy, the same length, they are identical in all ways, even though one Lewis structure isn't shown. So, this bond is identical to this bond, is identical to this bond. We need resonance structures to show us that. Brenna?
Are the formal charges partial charges then?
Are the formal charges partial charges? I would say when we get down to it, all of these are partial charges. Like, let's see. It's not a philosophy class, it's a chemistry class. However, if it were a philosophy class, what we would say is that these Lewis structures are at best a meager, simple interpretation of the true nature of bonding in any of these species. However, they're so simple and elegant, and they're 95+% correct that we'll use them. So, formal charges are hypothetical charges. If you remember way back, oxidation numbers were hypothetical charges as well. We use full charges because we don't know how to do anything else. And they're simple, but they're not real. They're useful. Sometimes they're real too, actually. Anyway, so, but what happens is we can only draw Lewis structures with octets or expanded octets sometimes, and the true nature of this doesn't have octets. That's the other part of it. So it's like somebody said, Lewis, in fact, said, let's draw structures for molecules. And it worked very well. And then somebody said, crap. How do we represent carbonate? And we said, oh, we'll come up with this funny idea of resonance, and that'll help us. Anyway, end of philosophy portion of the class, back to chemistry. These three bonds are identical. And on the exam, on the multiple choice portion, if it should show up, and it has before, if it said, is carbonate have single, single, double bond, you will say no. It has 3 4/3 bonds. They are not different. That's the point. Questions about that? See these? Do you think there's resonance here? Did we make choices as where we put the double bonds? We could have made other choices. Yeah, there's resonance. There's 6 resonance structures here by the time you put all of them, all the possibilities. And each of these will turn out to be identical. And what do you think they are here? Turns out they're 1.5 bonds. 3 halves. Anyway, so that's sort of where resonance takes us. All those bonds are the same. And that's almost always the case. Now, has anybody in here taken organic chemistry before? When you get to organic chemistry, you'll see that resonance, there is so much more to resonance that they'll teach you in organic chemistry, but that's all we get in Chem 4. Quick diversion or two. Polar and nonpolar covalent bonds. Well, so far, we've had formal charges, which help us to understand where the charges are in molecules. We've also had oxidation numbers, which help us understand what the charges are on atoms. in molecules. Now we're going to touch on polar and nonpolar covalent bonds for this portion. We will just identify or define a polar bond. A polar bond is a bond in which the two atoms have different electronegativities. I guess. It does say polar and nonpolar covalent bonds. So I guess I will write a covalent bond, which is a little redundant. A covalent bond in which the two atoms have different electronegativity values. And my abbreviation for electronegativity is capital E, capital N, and we'll see that. My example here is HF. I'll draw a big version of its Lewis structure. The fluorine will have 3 pairs of electrons around it. You will not only remember your electronegativity trends as you go to the left and as you go down, electronegativity decreases. But you will also have some of the electronegativity scores specifically for these two atoms. The electronegativity score for hydrogen, 2.1. For fluorine, 4.0. Think back to the most recent Olympics that you watched. Did anybody score a perfect 10 that you saw? My favorite is when the ice skaters do this. Well, fluorine is the perfect 4.0. That's as much as you can get. It is the most electronegative element. Neon, to its right, doesn't bond, so how can it have an electronegativity score? Well, maybe it does, but the one we'll see is 4.0 for fluorine. Delta En, which is the difference in electronegativity, will be 4.0 minus 2.1 or 1.9. And 1.9 is the largest difference in electronegativity that is still considered a covalent bond. Covalent means shared electrons. 1.9, that is a covalent bond. If the difference in electronegativity is 2.0 or greater, it's considered an ionic bond. If you go way back in your notes to chapter 4, you'll see a note that says hydrogen is always covalently bonded. If fluorine is the highest electronegativity score, then the difference in electronegativity can be at most 1.9, which is still quite good. Anyway, hydrogen is always covalently bonded. We said that back in chapter 4. I just said it again. Now, we will represent these two atoms as well, let's say this. Polar covalent bonds, the more electronegative atom attracts the shared bonding electrons towards itself. Becoming partially negative. Electrons are negative, you attract them to yourself, you become negative towards itself, becoming partially negative. The way in which we show partial negative, there will be two ways. One of them is to draw, this is a lowercase Greek letter delta. It's like a squiggly D with a minus sign. That means partial negative. You can also draw it like that as well. It's a lowercase Greek letter D. Anyway, I tend to draw it like that. That one's going to be partially negative because these two electrons are pulled closer to fluorine. If this one's partially negative, the other one has to be partially positive, creating a dipole. And a dipole is a permanent partial separation of charge. A dipole is a permanent partial separation of charge. And so now we have dipoles, which give us charges, partial charges. We have formal charge. We have oxidation numbers. We have so many different versions of charges. And in fact, dipoles are so important, we'll have two ways to represent them. One is with the partial plus and the partial negative. The other way is with what's called a plus arrow. And a plus arrow looks like an arrow with the plus on the back of it. The plus goes towards the partial positive atom. And the arrow points towards the partial negative, showing the electrons going towards fluorine. Now, I will typically use what I call plus arrows as representations of dipoles. Both of these are pretty common. What I like about plus arrows is that there's only one thing to draw. And as we get to larger and larger molecules, you will draw a dipole, a plus arrow, for every single bond. And so with larger molecules, you have more to draw, and it gets more complicated. Any questions about this?
Why that direction?
Why this direction? Is that what you asked for? The direction?
Stronger pull?
Right, so the arrow is pointing towards where the electrons go. So these two electrons are pulled towards fluorine.
So I might interpret it that there are more of them heading out there than the H.
Yes, and if we were back in chapter 7, we would say the bonding electrons have a higher probability of being associated with or closer to the fluorine. One of the take-home messages is that wherever there's a bond, when we get to later in chapter 9 and chapter 10, you can draw a plus arrow. Now, there are different ways of doing electronegativity. You will notice that I define it as whenever two atoms have different electronegativity values. So any two atoms that have different electronegativity values, you can draw a dipole. Anyway, we'll talk more about that. Now the blank space. What we're going to do here, let me think about this. Yeah, no, we were going to do this. We're going to take, the next one's blank too. What we want to do is we want to talk about something called skeletal structures. or line bond structures. Those are two words for the same thing. When you talk about, and you'll see this is much more appropriate a couple weeks ago during Halloween, but I couldn't quite squeeze it in. So skeletal structures or line bond structures, each carbon is a point don't show hydrogens attached to carbon. Because boring and to say one more sentence about it, carbon-hydrogen bonds almost never break, and they never contribute anything to our understanding of the molecule. Yeah, that might be taking it a little far, but they almost never break, and they're very boring. Each carbon is a point. Don't show hydrogens attached to carbons because boring. Any other hydrogens we will show, as you'll see. And what we get out of doing skeletal structures is that they're much faster than Lewis structures for big molecules. Let's start with a medium-sized molecule example. Something like this, where I'm showing all the carbons. For this molecule, we'll draw, since this is this will be the Lewis structure, it'll show all the atoms, all the bonds. Carbon will always have 4 bonds. Any bonds that you cannot see are to hydrogens. I'm already tired of drawing hydrogens. So that's an example of a Lewis structure with all the carbons, hydrogens, all the atoms, and all the bonds. Now, I guess there's one other thing, which is the carbon-carbon bond angle is drawn as approximately 109. And to make the analogy to next chapter, when we talk about bond angles, I'll put 109.5. I know, ridiculous, writing approximately and then having 4 sig figs, but I'm going to do it. Speaking of things that are not up my sleeve. Now here's what the skeletal structure looks like for this. See 1, 2, 3, 4, 5, 6 carbons? Watch this. 1, 2, 3, 4, 5, 6. That's those 6 carbons. I still have 2 more carbons to go. Just for effect, and since it's our first time, I'll number my carbons. But again, this is just so you can see them. 1, 2, 3. So I have 6 carbons so far. I have 2 more carbons attached to the 3rd carbon. So let's call this 7 and 8. 7, 8. And what you'll see is these kinds of structures are everywhere once you know what they are. And maybe if you didn't. You ever get one of those prescriptions? My favorite prescription is the Flonase, and it comes aside with the little distributor squeezy thing with this. You unroll it and it goes like this, and it's got all the contraindications and the indications. Well, it's also got a skeletal structure of the compound in there with all the atoms and anyway, you'll start seeing them everywhere. I know I did. about this. Bodie?
Why did you choose to take the carbon off that down?
Why did I choose to take the carbon off the 3 and go down? Well, there's no wrong choice, but there was more space down here, and I tried to keep them spaced out. Like if I'd gone up, it would have been between these two.
Okay.
So, but that would have been fine too.
But the reason it's on the third one and not the fifth one is because of the Lewis structure. It's on the third one.
Yeah. So 1, 2, third carbon has 2 other carbons on it. 1, 2, third carbon has 2 other carbons on it.
But it could also have gone up just as long as it's connected to the third one.
As long as it's connected to the third carbon, and all is good. Any other questions? One other example. I try to make big electrons so that people can see them from the back. Now, as I filled in those hydrogens, my number one thought was each carbon needs 4 bonds. Any bonds not shown are to hydrogens. So, I think I did it right. Yes. You'll see that in molecules, covalent molecules, there's actually on the ends CH3 groups. In the middle, there tends to be CH2 groups, and sometimes just a CH with another thing attached to it. Now, skeletal structure for this, 4 carbons, 1, 2, 3, 4. Oh, no, that's wrong. That says NH2 down there. So I'm showing all my H's that are bonded to other atoms like nitrogen and oxygen. Still not showing their bonds, that's fine. Question, Meredith?
So if I see you kind of made it a straight line, is it supposed to be a straight line or is it?
For this NH2? Yeah, no, so if I went straight down, I would have run into the chalkboard. So it's sort of a matter of convenience. If I had more room, I would have gone straight down to space things out. But it's the same molecule. Bodie?
What is the name of this?
What is the name of this? What?
Like the compound.
The system is called skeletal structures or line bond structures. The name of this compound? Let's see. I don't know whether, I think it would be 1, 2 amino, 1 butanol. Yeah, no, we're not responsible for names. You know when you're responsible for the name of that thing? Is the very end of Chemistry 401. There's a little unit on organic chemistry to prep you for organic chemistry and to teach you a little bit more. But you don't have to know any of the names. Here's what you have to know for the next exam. You have to know, if you look at a skeletal structure, you have to know that there's a bond between the O and the H, that this carbon has 3 other hydrogens around it, and good news, these ones you'll do 30 to 40 of them before we get to the third exam. So, good news, huh? Anyway, that's enough to do the Chapter 9 homework. You'll see that we have you going, I think, from Lewis structure to skeletal and skeletal back to Lewis structure for practice. And I think I did. I have another page there. Now back to our regularly scheduled programming. And for our regularly scheduled programming, we'll now hit polar bonds. Sorry, nonpolar bonds. Remember, a polar bond had a difference in electronegativity between the 2 atoms. A nonpolar bond is a covalent bond in which the 2 atoms have the same electronegativity. where I'm using capital EN for electronegativity. And it's simplest when the atoms are the same, then they have to have the same electronegativity. So, and nonpolar bonds, the bonding electrons are shared equally. And so for a nonpolar bond, there's no partial positive or partial negative to draw because they're equal. I'm going to say just a minute here about the dipole moments. The dipole moments is a more technical version of the partial charges we've been talking about. The dipole moment is represented by the lowercase Greek letter mu. It equals Q times R, where Q is going to be the charge. And R is the distance of separation between charges. Now,
As measured from center of an atom to center?
as measured from where to where, that's a very good question. Typically from the center of the atoms, but all I want to say right now is that there is a better way to assess the charges in molecules, the charges, but we don't have to know it. And if you have any questions, please do talk to me about this, but you don't have to know dipole moment. All we have to know is difference in electronegativity. So it gets more complicated, but we don't have to know. So delta En will be used in Chem 400 to assess the size of the charge. Damn it, I forgot one word. To assess the size of the partial charge. That's what we're talking about now. So we put in a little caret. The partial charge. Okay. And my last thing here, bonding a continuum. On one end, are nonpolar covalent bonds. And in nonpolar covalent bonds, two atoms get together to share electrons to complete their octets. No partial charges. On the other end are ionic bonds. With full on, positive, +1, negative, -1, +2, -2, etc. And somewhere in the middle, when the difference in electronegativity is 2.0 and over, these are all ionic bonds. All the way over to 2.0. Difference of electronegativity of 0, that's nonpolar covalent. And then all the space in here are polar covalent bonds, where the larger the difference in electronegativity, the more polar it is. And that's all the types of bonds we have in chemical theory. It's complicated. All right. Now let's talk about bond energies. And that is everything, actually, that we have to know about Lewis structures, about how to do Lewis structures, and now we get to use them for other things. And the first thing is going to be, well, actually, we'll talk about bond energies for ionic compounds first. And ionic bond energies are called crystal lattice energies. So if you want to know how large or how strong an ionic bond is, the crystal lattice energy, delta HCl helps you to do that. Now, crystal lattice energy reaction for sodium chloride has a specific reaction type. Do you remember the ionization energy reaction? It went sodium gas goes to sodium plus 1 gas plus 1 electron. That was what was called an ionization energy reaction. Sound vaguely familiar? I don't know. Well, this will be another type of reaction, very distinctive form. For sodium chloride, take a sodium ion in the gas phase plus a chloride ion in the gas phase. And our product will be sodium chloride solid. Now there is an energy associated with it. It's called delta HCl, and as of now, it's a mystery. But similar to what we did in Chapter 6, for thermochemistry, every single reaction we write has a delta H associated. We can do the same thing for magnesium bromide. Take whatever it is, put them in the gas phase. On the product side, have it be solid. More about that in a few minutes as we build our story. Now let's talk about bond energies for covalent bonds, bond dissociation energies. Each type of covalent bond has a typical or average energy for making it or breaking it, called a bond dissociation energy. This molecule, you could draw its Lewis structure. You could count up the electrons, put the single bond between them, make sure everybody's got an octet, and you would draw a Lewis structure like that. Now in the process of breaking this bond to create 2 chlorine, you break it and 1 electron goes with each of them. Side note, all of these species are in the gas phase. All of these species are in the gas phase. What we know about the gas phase is that gas phase atoms are far apart from other atoms, and they are essentially isolated, meaning they have no intermolecular forces, they have nothing, they're just all by themselves. alone in the universe. Universe. But that's why we're doing this, because there's nothing else going on. They're in the gas phase. Same thing. What's called the bond dissociation energy. Another way of saying that is the energy for breaking this bond. And for breaking this bond into two atoms, it's 243 kilojoules per mole. And if your question is, how do you know that? You will see a table called bond dissociation energies on your conversion and equation sheet, and it lists all of these. It says when a chlorine and a chlorine bond breaks, you get 243 kilojoules. Now, every single time you break a bond, the process is endothermic. Breaking bonds absorbs energy. Always true. 100% of the time. Lewis structure for H2. Delta H, BDE, bond dissociation energy. It takes 436 kilojoules per mole of bonds there. And here, I'm just going to leave it like this. 2 carbons, you break the bond between them. Whatever, the number is 347. It takes energy, it's all positive. Now what happens if I go from 2 carbons and I now bond them together? I make a carbon-carbon single bond. What do you think the energy is for this process? It's negative 347. The same rules apply. Flip the reaction, change the sign of delta H. It's not a bond dissociation energy reaction because bond dissociation breaks bonds. It doesn't have a name. So I'm just going to call it delta H reaction. And it's minus 347. And these are all tabulated for you. They are typical, meaning it doesn't matter how it happens or what else is going on, as we'll see. Now we're going to use bond dissociation energies to estimate delta H reaction. Here I have 2 things reacting to form HCl gas. I will draw their Lewis structures. I will draw the Lewis structure for the products, product in this case. And I have 2 of them. And just to estimate delta H reaction, here's what we're going to do. We're going to break this bond. We're going to break this bond, and we're going to make 2 of these bonds. To break this bond takes 436 kilojoules per mole. To break this bond, break the bonds. And if you look elsewhere on that sheet, to make an HCl bond, first off it's negative because making bonds is exothermic. Why do bonds form? Bonds form because the two atoms lower their energy when they make a bond. Always exothermic. And it's per mole, and you're doing twice as many of them, so the 2 shows up there. I'm doing this math in my head. Hopefully it works out. 679. So to break all these bonds, it takes 679 kilojoules per mole. To make all these bonds, that you get that much energy back, the entire process has a plus there. This much energy to break them, this much energy to make them. Overall, delta H reaction is from the minus 183 kilojoules per mole. So a couple things about this. One is, the way I remember it is, breaking bonds always positive, making bonds always negative. When you look on the list is all for breaking bonds because they're bond dissociation energy, so they'll always be positive. You have to remember to insert them in this. Next, once you do that, you add up the results to get your final answer. Does anybody remember delta H reaction equals delta HF for products minus reactants? I know it was the last exam, and you're allowed to forget it until the final. But anyway, the 2 have minus signs in different places. Good luck with that. Okay. Anyway, and so 2 other words about this, 2 other phrases then. This process is totally hypothetical. You can't just break all the bonds, toss the atoms up into the air, and catch them and make bonds on the other side. But that's the hypothetical process. Break all the bonds, make new ones, get an estimate of delta H. It's not true, but it works pretty well. And it works very well when everything is in the gas phase. Because gas phase has all the atoms already and all the molecules fall apart. It is not so good for liquids and solids. Okay. I think those were my 2 clauses or phrases, so I'm going to stop there with that. Any questions? On your homework, you will do this exact same process for combustion reactions. One of them says, using bond dissociation energy values in TRO or on the conversion and equation sheets, calculate an approximate value delta H reaction for the combustion of liquid acetic acid. And so what you'll do is you'll write a combustion reaction. You will write the reactants and products. You will write the Lewis structures for everything, count up all the bonds, and estimate the energies of each of these bonds. Just like we're about to do. Let me advance the slide. There we go. Estimate delta H combustion for the combustion of butanol and compare it to the value obtained using delta HF values. Well, you don't have to know what butanol is. But, does anybody remember how many carbons that has though? 4 carbons. AN, are the carbons connected with single, double, or triple bonds? All single bonds. OL is an alcohol. 1, 2, 3, 4. Put an alcohol on the end. That's still 4 carbons, by the way. This last line here is a carbon-oxygen bond. Common mistake is to think there's 5 carbons here, but there's only 4. If we count them up, there must be 3 hydrogens there, not that we saw them before. Feel free to draw them in, though, if it makes it simpler. like so. This formula becomes C4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. Combustion reaction says, put it with oxygen, have the products be carbon dioxide and H2O gas. Balance it. We've balanced things like this before. Put a 1 in front of the butanol. 4 for the carbon dioxide. And 5 for the H2O. That gives me 8 and 5, that's 13. We need 6 oxygens. So the first thing you have to do is balance it. And then you count up all the bonds. And to do that, you need to draw Lewis structures for everything. In oxygen, that's O2, what is the bond between the two oxygens? Is it single, double, or triple? Do you know? If you don't know, could you draw it? Doing Lewis structures, count up the valence electrons, bond them, that's what, it doesn't matter if you know off the top of your head. It's nice, but then do you know how to make it? Because this is an instance where you need to draw Lewis structures. If you do, you end up with that Lewis structure, which does have a double bond. What you will see is that a double bond has more energy stored in it than a single bond. So the type of bond matters when you break it or make it. A triple bond has even more. All right, well, let's do the rest of these here quickly so we can finish this problem. Carbon dioxide has 2 double bonds in it. Water has 2 single bonds in it. All right. Believe it or not, here's how this process goes. I have 1, 2, 3 carbon-carbon single bonds. I have 1 carbon-oxygen single bond. That's that bond right there. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon hydrogen single bonds, and 1 oxygen hydrogen single. So you got to, this is the level of detail for this problem. And these numbers are all times 1 because the coefficient is 1. I have 1 oxygen-oxygen double bond times 6 as the coefficient. And I keep rolling along. I have 2 carbon-oxygen double bonds with an asterisk. Do you know that when you look at the bond dissociation energy table, there's actually 2 tables. One of them has all the single bonds on it between all the different types of non-metal elements. And then there's another table just for the ones that do double bonding. And then at the very bottom of that second table is an asterisk, and it says carbon-oxygen double bonds have their own special value. Turns out to be 799. You could call it a fudge factor if you want. Doesn't matter what you call it. Use it. Anyway. You have 2 of them per molecule. You have 4 moles of molecules. The 4 goes right there. Five times 2 for the water OH bonds. All right. Questions so far? If not, we'll roll right along. Carbon-carbon is 347. Carbon-oxygen is 360. So all I did is I looked at the table for all these. This is how much energy in kilojoules per mole. It's killing me not to write kilojoules per mole after each of these. I better do it. Yes. There are some things, some would say many, that I never would think of. 6 times 1 times 498. Again, looking up all the numbers on the periodic table. Four times 2 times minus 799 kilojoules per mole. That's carbon dioxide. Five times 2 times minus 464. We're almost done and we're almost out of time. If I add up all these numbers, I get 8,579. If I add up and multiply all these, I get minus 11,032. And then I straight add them, meaning this is positive plus this is negative, and I get my final answer.
First one is for all five?
Say that again.
Carbon and oxygen?
Sorry, say that again?
The first value, 8.79, is that for oxygen and?
That's for all of these with all their multipliers. Maddie?
And then is carbon, or is the oxygen included in the 11,000? Yeah, that was my question.
The O2, the 6O2.
Oh, yes, these are included in that as well. Sorry. Good thing I have 2 more minutes. Organization is key for these things. Working on it. All right. Try again. 8579 plus negative 11,032. Minus 2,453 kilojoules per mole as my delta H combustion. Now, if I were to do this using delta HF values, I would get minus 2,783. And you're like, crikey, that's crap, because it's 300 off. It's about 10% off, but I would suggest to you that that's not too bad. And this is a good way of doing things rather than actually doing the reaction. We're out of time there. There is one thing you cannot do on Chapter 9 homework. Everything else you can. Let me tell you what that one thing is. That one thing is what's called a Born-Haber cycle. If you see a problem on Chapter 9 homework that says Born-Haber cycle, save it for after Monday's lecture. Question?
So the delta HF values of the Born correctly is finding them? Or
The delta HF values are the more correct way. This is an estimate. The estimate is good when the species are gas phased, and but still, it's not perfect. Yes. Any other questions? For those of you who came in late, let me say one other thing. Next week's lab is lab number 10, followed by the following week by lab number 9, when we do have lab, and then the lab practical. All secrets to the lab practical discussed at the beginning of the lab 10 lab period. Emilio, did you have a question?
No, never mind.
All right, then we're done for today. Thank you. If you have discussion today,